Hi everyone. Thank you for coming to my talk. There are apps in apps, and here is how to break them. I'm Ronnie. I was previously a pen tester for many large internet companies and banks. Now I'm a web and Android security researcher at Tencent Security Shenwu Lab. Our research fields include Android, web, Windows, IoT, browser, etc. And we output many outstanding achievements such as BitTunnel. Here is the outline of my talk. First, I will show you what's outside and inside the Eastern app. Next, I will detail the architecture and some vulnerabilities of WebView-based Eastern app and native Android Eastern app. First of all, I should clarify some keywords in the title. The first app is called Instant Apps, and the second one is Supervised Apps. Okay, let's get started. Maybe you have no idea about the form of Instant Apps. It's an emerging new draw and is developing rapidly. Since the rise of mobile application, many internet companies released their mobile web adaptation framework, such as Instant Articles of Facebook and Google AMP. And then there are many mobile hybrid development frameworks bringing better interactivity. And finally, Google Play Instant App was released on Google I/O 2016. This represents the birth of a new form of mobile application, and then various WebView-based instant apps are released immediately. Apple also released their own instant app named App Collapse at WWDC 2020. Here are some screenshots shows what internet apps look like. They are widely used in Asia. In the first two screenshots, typing one button can start an instant app from Instant App Center or search box. And in the third one, someone shared a link in the chat window. Tap on it will start an instant game app. The last one is a game with support for Google Play Instant. Tap on Try Now to play a part of it. No need to install. What's inside, you may ask? There are two common architectures. The most popular one is based on WebView. From a developer's perspective, it's a very flexible way to develop hybrid mobile apps. Unlike traditional hybrid apps, instant apps can load and run remote modules provided by a third party. Let's compare the WebView and the WebView-based instant app. I will call WebView-based instant app as WBIA for short in the next. The left is a model for the WebView apps. Its rendering and logics are all implemented in WebView, and you can directly access external resources from inside the WebView. On the right is the WebView in an instant app. It's highly isolated. The most different is that it can't get any data or remote resources unless communicated with JSBridge. Next, I will detail the architecture of WBIA. Let's look deeper into the WebView in WBIA. The application is based on the JSBridge framework. The render layer is implemented in DOM windows. Compiler and packager will translate the source code, XML, JSON, CSS, etc. to a rendering template. The template needs binding data from logic layer to make itself an available page. The logic layer is implemented in the service worker. As we know, a service worker is a background process independent of DOM windows. In general, there is only one service worker per domain, and all the pages of the domain share it. So the packager should package all the source code, mainly JavaScript, to run in a service worker. The most common choice of packager is Webpack. The logic of each page is packaged into its own Webpack module. Generally, there is only one service worker per domain, so One instant app is one domain. That's the necessary condition for isolation in the web view. Overall, we can abstract the communication between an instant app and JSBridge to multiple domains and JSBridge. As you can see, the isolation between domains is supported by WebView. Bypassing the same origin policy directly is very difficult, so our target is JSBridge. In this classic WebView, there are two most frequently used methods to do this: and JavaScript interface and WebView event handler. But there are some features that are hard to implement with classic WebView in the instant app environment, such as process isolation, async communication, etc. The common WBIA architecture provides two solutions for them: cross-domain communication with privileged domain and event handling framework. Let's look at a graphic about JSBridge in WBIA. Only privileged domain can communicate with JSBridge, and the instant app domains should initiate cross-domain requests for calling JSBridge. And the event handling framework deals with comparison and asynchrony among three paths. Next, I will show you some attack surface and vulnerabilities in WBIA. Firstly, our target is lateral movement, compromising isolation between instant apps to steal data from other instant apps. Go back to the JSBridge. Obviously, there are two potential attack surfaces. Where do requests come from, and where to send the response? In other words, attack surfaces are JSBridge request identification and event callback. In this talk, I will only detail the first one. There is a key data structure in the identification: app ID and WebView ID map. The following graphic shows the process about handling JSBridge requests from WebViews. At first, the supervisor app gets the WebView ID according to where it comes from. Then it searches the key map for corresponding app ID. The hit app ID specifies which instant app is calling the JSBridge. But the above is only an ideal situation. During reversing, I found the first bug in an instant apps platform. I found there are some specific parameters can lead to lateral movement. For example, if you add an app ID parameter in your privileged domain request, the supervisor app will let the input parameter override the original app ID from the key map. The first bug is very simple. Unfortunately, not all instant apps platforms are so fragile. In most cases, there is no parameter we can inject to confuse the supervisor app directly. In the talk above, we focus on the instant app implementation on the client. Instant apps communicating with the supervisor app for data transmission. But that is not the end of the process. Now we introduce the third part, the backend render server. The graphic shows the whole RPC process. Supervisor app calls RESTful APIs of the backend server, then get response data. Finally, decode data and trigger instant apps callback. During reversing, I found an interesting kind of RPC implementation. I call it XRPC. The biggest difference from ordinary RPC is the internal process in the supervisor app. It receives a parameter as a RPC interface name. Then it instantiates this interface and passes the controllable parameters to the interface function. Finally, the interface function will call the RESTful API and get data from the vendor server. It means that we can control the supervisor to call any API with any identity by XRPC. Although we highlighted that communicating directly with the privileged domain may lead to compromise and isolation, it's far from the actual exploit. This is the life cycle of an instant app. First, developer writes and uploads source codes to the vendor server. Then the backend server package and compile those source codes and release the packaged instant app. Finally, users type a link on the mobile phone. Then the instant app will be downloaded and started automatically. There are two difficulties in the exploiting. The backend vendor server will package our payload in the remote black box. Besides the security check and filter in the server, the packaging process itself will be also modify the payload. And in the client side, our payload will be loaded into a sandbox based on Webpack. There are some limits for initiating cross-domain requests from our payload module. At first, there are two common methods for cross-domain requests: fetch and import scripts. Fetch can't get response without specific HTTP response headers, and import scripts can be only used in Service Worker. Our target is to access any one of them, and import scripts is better because our module will be loaded into Service Worker and the import scripts can get response directly. Our payload will be packaged as some modules in Webpack. There are two main limits: objects blacklist and objects localization. Blacklist works at the stage of packaging. If you write those sensitive functions and objects in your source code, those objects will be released to world 0, none or undefined. As I just said, Sandbox is based on Webpack, so how Webpack organizes his JS bundles? That's a demo of a simple Webpack project source code. It has three main source code files: Webpack config.js, index.js, and sum.js. After packaging, the files index.js and sum.js will be packaged as two modules into bundle.js. The module 0 is index.js and the module 1 is sum.js. We can see that in the index.js module, sum.js will be loaded by function webpack require 1. So we can research all the installed modules for the one export global object. Although our codes are obfuscated after packaging, we can use the third argument to call webpack require. Another limit is object localization. Some sensitive objects will be moved into a private module, become local variable. In practice, this limit is usually implemented by following pseudocode. It replaces the function in the proto of the global object. But we can recover it from the prototype chain. In the Service Worker, the global object is an instance of the Service Worker global scope, and the function import script is inherited from worker global scope. If that class is not in the blacklist, we can use the following code to recover the function. Finally, combining with the vulnerabilities we found and the dev life cycle, this is our exploit flow. In the About talk, I detailed the architecture and vulnerabilities in the WebView-based instant app. There is a totally different architecture based on native Android IPC. The most representative implementation is Google Play Instant. That's the introduction from Office document. Native apps without installation, and you can use it anywhere you share a link. By reading the document, I learned that the Instant app is a real native Android app based on app bundle publishing format. That's very cool. After reversing, I got the following conclusions. At the API level greater or equal to 26, Google Play Instant is supported by AOSP. Compromising it will be more difficult than local privilege escalation from app users. But to be compatible with versions below API 26, Google Play Service provides a package named COM Google Android Instant Apps Supervisor. That's pretty good. Let's go back to our familiar area and look at the inside of Supervisor. This graphic is a little complex. There are three main parts. At the right side is isolated processes running the logic code of our instant apps. And in the middle is the supervisor process. At the left is the system resources accessed by the supervisor process. The isolated processes of instant apps will be initialized as a service, and the supervisor process will start a shadow activity filled in with the corresponding instant app. There are two important proxies for the isolated process to access systems interface. IPC proxy is to transmit the IPC request from isolated process to Android system service. And the syscall proxy is to transmit the syscall from isolated processes to supervisor process. Generally, it means isolated processes call libc method. For example, I want to open a file in my data directory from an isolated process. Because of isolated user permission, it should be forwarded to syscall proxy and call open method as supervisor app. Next, I will detail how those proxies work through reverse engineering. First, you can find the setup process by a systrlib named setup with application info. During the setup, a supervisor app registers three binders for an isolated process. The first one is named IPC.ServiceManager Forward I call it IPC proxy for short. The second one is named syscall.syscallService. That's the syscall proxy we just said. The third one is named Event Receiver, used for event callback. Next, let's see how IPC proxy works about access control. There is a main configuration file named DNA data at the app's data cache directory. It's always loaded from a zip file with a strange file name, like this. The DNA data saves the whitelist configuration about IPC in protobuf format because it removes the symbol information of reflection. It's very difficult to passing the protobuf configuration by reversing. So I decoded it directly at the general protobuf data structure. Then I found there is a big list of AIDL items. In the AIDL item, the first field is AIDL class name. The following field is an alias name for it. And the third one is the class name of the proxy handler which forwards the IPC request sent to this AIDL. And the 10th field is a repeated field of IPC method item. In the IPC method item, the first field is a nested data saving the method's signatures. In the method signature item, The first field is method name, and the following field with tag 3 means the method parameter steps. It's an enumeration type. For example, 5 means int, 9 means string, 13 means class embedded, and the field with tag 4 means the method return type. And there are some other fields following. Maybe they mean some flags or parser typo we don't care about. The last field of the IPC method item is very important. It means the permission type of this IPC method. If the type is greater or equal to 3 and less or equal to 14, supervisor will raise a permission check field exception when isolated process is calling this IPC method. Besides that permission type check, the following flow chart shows how IPC proxy check an IPC request. The isolated process initiates an IPC request to a system service. Then the supervisor will check if the corresponding AIDL has a proxy handler. If it has, supervisor will check the method permission type, and if the proxy handler has a public method with the same signature, the IPC request will be forwarded to it for security check. Otherwise, requests will be sent to system service directly by supervisor. Finally, let's look at the Syscall proxy. It's implemented in libsyscall. Because it's a banner, it must have an onTransact method. After reversing, I found the function entry and there are 88 transact code for banner call. For example, the code 0x38 is libc open. Next, I will show you some vulnerabilities in Google Play Instant. Google Play Instant app looks much like a native Android app, and it can run on your phone with a tap. So it's dangerous to let it directly access any components outside the supervisor app. Obviously, the development team has also thought about it. There is a sandbox for access external components from Instant apps. An Instant app can only access its own service, broadcaster receiver, and the content provider. As for activity, supervisor will forward starting activity intents from Instant apps. The payload in the intent will be relocated in a new field. In order to expand the attack surface, we have to bypass the sandbox to access external components without limits. When I read the check logic in the proxy handler, I found an interesting class named IntentSender. Although the IPC method getInstantSender will be checked and forwarded by the Activity Manager proxy handler, there is an interesting parameter can help us bypass all checks. SendIntent is a public method of class IntentSender to launch itself. The parameter intent will be passed to the method fill-in. That will make the input intent override the original intent saved in the IntentSender. So there is an escape route from the sandbox. First, get an IntentSender in whitelist by IPC call. Next, initialize a new intent with target component. Finally, use method send or SendIntent to override the intent of the original IntentSender. Besides above, there are some other vulnerabilities in Google Play Instant. For example, a duplicate provider authority leads to compromising the access limit of external content providers. Okay, that's all. And thanks for your listening.